So you've told us a lot about the Air Force Processing Science Program. Were there any other important or influential government programs that you worked on during your time at Battelle?
Yeah, being at Battelle, and having a great laboratory capability and sort of helped us get other government projects that involved, a number of things that I can't talk about, but helped me broaden myself with regard to material systems. We did a lot of work for the Department of Energy, looking at uranium-based materials and uranium metallurgy. So we worked on sheet fabrication, we worked on extrusion operations. Again, those rolling mills that we had for intermetallic alloys like gamma-tide aluminides were also useful for making sheets, various ordnance-type materials. I remember, developing pack rolling processes for Albumet and aluminum beryllium mechanical composite. We did extrusion of round rods, also of depleted uranium-based materials, and the approach we took for titanium or for any material system was very similar, and it emphasized the importance of understanding physical metallurgy, phase equilibria, and kinetics, because everything in processing, comes back to what are the stable phases. Is it single phase or two phase? What limits the workability? How do you control the microstructure, and how's that microstructure, control the properties? So it's very classical metallurgy with an emphasis on the processing of things, because if you can't make it well, you can't put in service, and you can't, assess its life, its behavior and lifetime. So in conjunction with, working some of these exotic materials, I also had the chance to work with some of the best people in the characterization area that I've ever known. Even though our equipment was nothing like what we have today, we were working with a Bausch & Lomb Research 2 optical metallograph. Even if we had a B&L 1, getting polarized light micrographs of uranium, for instance, was really difficult. A lot of the photographs that we made ended up in handbooks. Also, with regard to some of the other government work, we did a lot of work on assessing foreign technology. Much of the work we do at the Air Force involves not only involves developing new technology, but knowing what other people are doing to prevent us from being leapfrogged. So I had the opportunity to work quite extensively at assessing what other people were doing around the world. And once in a while, we would get something that we could look at, a product that we could look at to see how others were doing things similar to what we were doing. So it's very, very interesting to understand how people think and how people approach development of new materials and processes. About the same time, that I was working on the Air Force stuff, however, I got to know the people at the Air Force quite well. Not surprisingly, both we'd had projects through the Air Force Office of Scientific Research in the early '80s. Then we had the Processing Science Program in the late '70s, early '80s. After those were over, I started spending more time as an adjunct professor at The Ohio State University. And coincidentally, one of the master's students I worked with was the son of the chief scientist of the Air Force Materials Lab. The son's name was Paul Byrne. His father was Harris, but he was the chief scientist of our lab for a number of years. So he and I was working with Paul, his son, on his master's thesis in a topic related to interface heat transfer during forging. And that provided the opportunity for me to get to know his father, Harris Burt, much better. Harris, as a matter of fact, had been a big champion, along with Alan Rosenstein at AFOSR, of the Processing Science Program. And I knew Harris through some of our annual meetings for the Processing Science Program. So when it was sort of coincidental that I would be his son's thesis advisor in the late '80s. Alan Rosenstein was a big mentor to me. And I think it was beginning in '87 or '88, they started saying, Lee, why don't you consider coming to work for the Air Force? I think it was 1989, 1990, they convinced me to spend a part-time sabbatical where I'd go 2 days a week to the lab at Wright-Patterson Air Force Base outside of Dayton. just to see, get the lay of the land, so to speak. And I had the opportunity to work on gamma-tide luminides, which was still a pretty hot topic with regard to the National Aerospace Plane Program. And I said, this is a pretty nice laboratory. You know, of course, I'd been there before, you know, while we were working on the processing science program, but I actually had a lot more time through this visiting scientist effort to see how it worked. So after a couple of years, you know, Harris came by, and my predecessor as a research leader, Jim Malice, who himself had succeeded Hal Gagel, who was one of the guys involved in the early processing science program days, said, why don't you come give us a talk? I didn't realize that talk was actually a job interview. I think it was 1990. They said, no, we'd like to make you an offer. And after thinking about it for a few months, I accepted it. Even though there was a hiring freeze, they managed to get my application through, and 8 or 9 months later, I was there at Wright-Patterson Air Force Base in what was then called the Materials Laboratory of Wright Research and Development Center. There's been numerous name changes over the years, but it's always been part of the Air Force Materiel Command.
So when you joined the Air Force, tell us a little bit about some of your principal research activities when you first arrived.
Well, when I first arrived, I was actually hired to be the research leader of the metals processing group, or materials processing group, because we did more than just metals. We did MMCs, some CMC processing, non-metallic polymer processing, with a heavy emphasis on metallic materials, of course. I was hired in as a senior scientist, you know, it was like a GS-15. We hadn't transitioned into the so-called lab demo operation yet. But I was given sort of like carte blanche to organize the program, which was nice. And also it turned out that the building that we were in was only 3 or 4 years old. Our lab during '91 has started transitioning from an old building, which was eventually demolished, to the building that we're in now. So I was put in charge of overseeing the moving of equipment and the setting up of the lab. So that was very nice, not only to have the responsibility and some of the authority for the research itself, but also to oversee, you know, how the lab was constructed, how the layout was done, you know, in conjunction with some of the other government folks, of course. It turns out that even when I was at Patel, one of our government projects had been to make recommendations for purchase of a forging press, a new forging press. So I knew exactly, since myself and Tylenol had written the spec for the press that was bought by the Air Force, it was sort of coincidental that the 5 or 6 years in between us speccing the press and my joining the Air Force was, you know, it took that long for them to buy the press. And I think 6 months after I got to the Air Force, we had a hole in the ground and the press was being delivered. Also, some of the equipment that initially was going to be thrown out, I managed to save, thank goodness. And we were able to get extra space for the lab, which is in a high bay area. And so I was very fortunate to be able to set up some of that equipment. Also, I had the responsibility for not only, you know, setting up the prototype production scale equipment. We had like a forging press, extrusion press, rolling mill, but also we started building new capabilities, especially in the area of hot workability. So we undertook to build an advanced hot compression system, a new torsion testing system, as well as, you know, looking at new characterization tools. I think we were some of the earliest users of, for at least aerospace alloys, applying electron backscatter diffraction methods to titanium. The overall program was basically broken into 4 major areas. One, the bread and butter was developing material behavior models for processing of aerospace materials, mostly tie and nickel conventional alloys, A lot of it had to do also with intermetallic alloys, because this was still during the time when NASP was a high visibility, highly important program. So developing the models of microstructure evolution, defects, not only for the intermetallic hard to work alloys, but also for the conventional alloys, and texture evolution. So that was probably the main thrust of our research, that I was said, make sure we're strong in that. Because the Air Force has its own, sometimes people refer to as niche materials. There's not a big driver, there's not a big commercial tonnage production base to support research. So one of the reasons why we have the Air Force Lab is to make sure we get research done, and we fund extramural programs to make sure our materials are the best they can be. So that was half our program. The other parts of the program was to both develop and to characterize novel processes. Thirdly, complementing the material behavior models was to develop advanced computational techniques for simulating microstructure evolution. And lastly, we had to develop some of our own advanced characterization techniques. So those are the four major areas, and those 4 areas probably is work we've done since 1991 to the present. It's evolved over time, but that's been the basic thrust.
So throughout your earlier years, you talked a lot about interactions with industry and transitioning practical, pragmatic models to industry. Can you describe how that continued in the Air Force?
Yeah, that's a good question, Adam. One of the nicest thing and one of the most attractive aspects about working in our lab is that the laboratory handles not only its own in-house research, and we're very well equipped for that, and both equipment-wise, as well as a wonderful technical staff, a number of PhDs and master students, and great technicians, but also we manage the extramural program. In other words, some of our funding, especially our advanced development or 6.2 funding, goes to companies, sometimes universities, to do research that parallels our research, but also takes it the next step in the development. In the air processing, we've had a number of contracts to develop, to take some of our basic knowledge and actually try to do it on an industrial scale. One of the biggest contracts we've ever had has been the so-called Metals Affordability Initiative. I think it got started in 97 or 98. And the objective of that contract is to help develop and demonstrate new processes and new alloys. And that's been a very successful project or program over the years. So when having our own in-house research, we want to transition new ideas, but at the same time, it's a two-way street. When industry does something, not only for MAI, but for anything that they're doing for the government, oftentimes there's a challenge. We learn what the technical challenges are, and that helps us. There's a feedback loop. It's not, it goes both ways. We learn what things may need basic research. At the same time, we're motivated to try to do the early development work that will help make the eventual industrial project more efficient. And that's probably one of the nicest things about working at the lab. Right now it's called the Materials and Manufacturing Directorate, is that we can do this stuff jointly with our team members in making better products for the Air Force. So an example of that would be work we did on developing models of the behavior of titanium during forging. Now, that was a project that we did with a forging company, a titanium company, and an academic partner, among others. Now, it was a project that ran 3 or 4 years. We developed some of the basic understanding of plastic flow of two-phase structures, microstructure evolution during forging and heat treatment, and developing models to describe all this stuff. So there's been numerous incidences where we work, where we do integrated integrated work with industry, or where we do some initial work and it's transitioned to industry. And I can tell you, there probably been in my lifetime and at the Air Force, I would guess a good 20 or 30 times where something we do has been spurred by something we've seen in industry, or a need expressed by industry, or something that we knew could be done jointly with industry. One of the nice things about our lab, since we have prototype production scale equipment, is that we can do something a lot more simply on our production scale equipment than you could do in a real production environment where they can't take equipment offline. A lot of our equipment also has very special sensors and control technologies to enable us to do things that are sort of novel. So good examples of that would be things like developing some novel forging processes. Also, we've done a lot of work on developing, looking at severe plastic deformation processes, equal channel angular extrusion being an example, where we built our own tooling and we demonstrated some of the pros and cons of the process for refining microstructures. We've done a lot of work on thermomechanical processing. We've also done a fair amount of work on other states of matter, including vapor processing and solidification processing. Vapor processing, for instance, we did work on looking at the effect of coatings, making coatings by plasma spray or electron beam physical vapor deposition for making coatings for engine blades, for instance. In the area of solidification process, I think we were among the early groups to look at SPD techniques.
So Lee, you've described a lot of your work in thermomechanical processing, forging, heat treatment, rolling, extrusion, etc. Are there any other processing methods that you've worked on?
Yes, we've done some what I think are key problems in the area of both solidification processing and vapor processing. So we've addressed all three states of matter. For instance, in solidification processing, we've looked at novel techniques to melt material, such as the EB cold hearth melting, looking at alloying element losses, and developing models for instance, loss of aluminum during hearth melting of Ti-6-4, titanium 6 aluminum 4 vanadium, associated with working in a vacuum. We've looked at the effect of process variables on surface finish in the EB hearth melting process. One of the things that I'm most proud of is our early work on additive manufacturing, basically a micro-cast melting and solidification process. I think we were among the first to develop processing maps or processing know-how for additive manufacturing of titanium alloys. This was in the 98 to 2002 timeframe. We were working with mostly with powder injection methods where you have a light source such as a laser and you inject powder particles on it to melt that incrementally, layer by layer. So we did work with a small equipment manufacturer, Optimec, on the lens system. We worked with a larger scale-up system using a CO2 laser to do laser additive manufacturing. The person who worked on that was Pam Coburn. She led a lot of that work, and it was sort of fortuitous because she had done her PhD on permanent mold casting of titanium. So she understood the effect of process variables on the equiaxial to columnar transition, and that was key in a big cast part. So that was key to understanding what happens when you do micro melting and micro solidification in the lens lam process. It's also applicable to the newer or the more recent used processes that are based on powder beds. So it was very nice that Pam was able to take some of the knowledge she had gleaned from permanent mold casting of titanium, in which you cast into a metal mold rather than more conventional ceramic investment casting process, and show why in some of these processes you almost invariably get a columnar grain structure. So coupling knowledge on these different, taking a more generic approach is, I think, a hallmark of our work. We're not necessarily studying additive processes or casting process per se. We're trying to get a unified vision or understanding of what happens when you go liquid to solid, what happens when you put work in the solid state for a thermomechanical process, or in the case of a vapor process, what controls the structure and the defects. The vapor processes are very important for coatings. Now, we've looked at plasma deposition of coatings, but we also spent a good deal of time looking at electron beam physical vapor deposition. Example of that is our both single layer as well as multiple layer coatings on nickel substrates, for thermal barrier coatings. We've also looked at the process of EB-PVD with partners in Ukraine to make thin foil products. Thin foil is a very important aspect of making thin structural components, such as thermal protection systems. So we worked with them to demonstrate that we could make foil products a lot, we demonstrated the technical feasibility and showed that economically it's a lot better to do that than to take a big ingot and work it down to a sheet and then to a foil. So those are a couple examples of vapor processing. But again, the aspect was partly to show that we could take EB-PVD or magnetron sputtering or something like that. We want to show that we can make the product, but also what were some of the process variables that are important, and how can we take this generic knowledge to fill it into a unified understanding of vapor or solid state or liquid to solid state transformations. So there's always been this fundamental knowledge, desire to get fundamental knowledge, but the end has been, can we then take this knowledge and make a product from it? So rather than trying to just do something by editing approach to make a product, we want to understand what limits our ability to control structure, defects, crystallographic texture, and so forth. And that sort of permeates everything we do. And with that basic understanding, we're also able to get a better handle on development of material-sensitive models. And a couple examples of those models I mentioned, as I mentioned before, the basic material behavior modeling techniques are things like Monte Carlo modeling of recrystallization and grain growth. Another example would be cellular automaton type techniques. In our case, we used to look at recrystallization problems also. A third type category would be the crystal plasticity FEM techniques, where we want to be able to simulate not only the evolution of deformation texture, but also understand how deformation may bias a transformation that occurs following high temperature heat treatment. So the Monte Carlo technique, we've tried to apply that to mostly to tie and nickel alloys. One of the limiting factors that we've always known is the dearth of good input data, grain boundary, energy mobility, and so that if I say that that's one thing that we really could do a better job on. That's an example that a number of our staff members have fallen on their swords trying to get some of the input data properties. Cellular automaton, I think we demonstrated, very, very well why you get different types of flow curves during recrystallization problems. CPFEM, I think, has been one of the most successful aspects, both for deformation textures, but as well as for transformation textures, as well as some of the crystallization problems. I think we're both very interested in long-term getting a code that will work not only on a research scale, but also for transition to industry for titanium alloys. Again, we're talking about codes that will give us a 10 or 20% error, because we fully realize that if we try to transition a code that just gives you qualitative guidance, it's not going to go anywhere. So developing of these modeling techniques, be they crystal plasticity or some other technique, requires a very careful calibration and validation to get them to be transitioned to industry. So if I learned one thing over the years, it's that we have to make sure our models are so-called industrial strength, that they work within reason and give you an answer to a problem that is too hard to measure, and the modeling would only, you need modeling techniques to avoid excessive trial and error experiments. And so with that background in the 1990s, that's naturally evolved into work to integrate all this understanding.
So you've just described an incredibly impressive career. If you had to summarize some of your key accomplishments throughout that career, what would they be? Well,
I think it's like saying, who is my favorite child? Okay. And again, when you say my career, it's been our career, our team, our group's career, our colleagues' career. I've been fortunate to work with so many wonderful people, not only wonderful technical people, but people who are friends. I think we look at what's happened in the area of processing over the years. The evolution of what we now refer to as integrated materials engineering or integrated materials science and engineering. This did not happen overnight. It's been evolving for the almost 40 years I've been in the area of processing, and so I consider that part of an evolutionary thing, and we're constructing an edifice to help industry by incorporating and integrating tools. So I would say the microstructure, defect, texture tools that we've worked on, I would say that's one of the major things. The introduction of new processes and the tech transition, teaching industrial partners what can and can't be done, has been a major accomplishment of our team. And I think just developing a mindset to get people interested in processing and understanding the need to couple processing knowledge with behavior and life prediction, I would say that's a very important. I was very happy to make a contribution to that. It's just I've been very lucky, and again, without a good team, without good coworkers, all of whom I think hopefully have some fun, although I've been known to be somewhat of a taskmaster at times, especially when it comes to writing and communication. It's been fun. Without those friendships, though, and the help of family during hard times, family and friends, none of this would have been possible. I've just been very lucky. And also, I must say, I've been very fortunate to have had the opportunity to work with technical societies. The TMS, ASM, they've all been very helpful in developing these contexts that we've talked about. A couple examples of that have been, I remember putting together co-organizing my first symposium, which dealt with shear bands and forged products in 1980. It was held in Chicago, I think, or Rosemont, whatever that little suburb of Chicago is. So having the ability to develop symposia, and work within the committee structures has been very helpful, not only to develop me as a technical person, but also to meet other people. So the TMS and in some respects, some of the other constituent societies of AIME has been very useful to me. And with regard to other societies, ASM, I've had the opportunity to work on a number of handbooks for ASM, a number of topical symposia proceedings for TMS. All these things, networking people, organizing information for use by others has been a very enjoyable experience. And I would highly encourage our young members, be they TMS, AIME, or any other society, to take advantage of the opportunity that we have, to work on a committee, to work on a conference, organize a topical symposium, to start something new, because the society is only as good as its members. You know, we're helped out quite a bit by the administrative staffs, but we are the society, and it's up to us to continue the tradition. You know, when I think about TMS, I remember my days at Carnegie Mellon going down into the basement and finding these dark purple lavender volumes of TMS AIME, oftentimes, you know, blowing the dust off them, you know, from 1910, 1920, and so forth. I'm saying that was classic research.
So Lee, you're a very modest man and not one to toot your own horn ever, as long as I've known you. But have there been any great personal recognitions you've received throughout your career?
I think, well, I've been very fortunate that our work has been recognized. I think in my early life, I think the work we did on gamma thiolumides with Rockwell International as part of the NAS program was a very nice recognition. They gave me this little artistic rendering of the National Aerospace plane, like a little wooden model. I still have it on my bookshelf at home. That was really nice. I think the recognition that I've gotten at Battelle for some of the process development, some of the patents, and seeing them introduced has been very heartwarming. Both TMS and ASM have recognized some of our work through awards such as the Bruce Chalmers Award and the Albert Savur Award, and then the ASM Gold Medal. I think from a team standpoint, 4 or 5, 6 times AFOSR has recognized our work in-house through the Star Team Awards. And I think it's really been appropriate because of what we're doing as a group effort, and being anointed, so to speak, as a Star Team by AFSR is a high honor for all of us. And most recently, I started out as an engineer in high school, and most recently I was inducted into the National Academy of Engineering. It's sort of like my life has come full circle. I started out working in the practical foundry and forge in high school, and being inducted into the National Academy of Engineering was something that one always may dream about, but very few of us get recognized. So having that recognition was very touching, and especially when I see who else has been elected, and also it's very nice because it's indicative of the fact that we in the government lab are doing something useful, not only for engineering, but also for our country and for the international community, because a lot of our research is basic and it's science and engineering. So being able to again, use the science to solve engineering problems has been a main theme of my life, my professional life. And so to be recognized by the National Academy was very nice, and I'm very appreciative of that. And I hope that our staff realizes how much I appreciate their work, and that this really has been an important part of my life.
So you mentioned that there's excellent scientific staff, wonderful technicians working at the Air Force Research Laboratory, but I also know there's a lot of students there. Can you describe some of your interactions with some of the students?
Yeah, we've actually had a number of students I've worked with over the years, both undergraduate and graduate students. The undergraduate students have been largely from University of Dayton and from Wright State University, a few from Ohio State, and I'm adjunct professor at all 3 of those universities where I work with the graduate students, but these undergraduates work part-time in our lab, and they actually do some of the grunt work. At the same time, they get to see what real-life research is, that it's not something you just, it involves a lot of perspiration. I remember, I think it was Edison's well-known aphorism that invention or genius is 1% inspiration, 99% perspiration. So it's very easy for somebody like me to have the inspiration, but still we got to put in the perspiration the sweat. And so I think I probably have had the order of maybe 50 students-ish working with me over the years from the different universities, even some from, most of those students are mechanical engineers, some are materials engineers, some are physics majors, some are chemists. We even had a pre-med guy from biology to whom we assigned work dealing with characterization of microstructure using automated techniques.
But they all sweat when you come in for a notebook check, right?
Ooh, guilty as charged. That was a low blow at them. Yeah, one thing we teach them besides how to work in the lab and how to get good data, but also how to organize their thoughts and their data. And one of the things I used to do in the pre-electronic age was to make sure they had lab notebooks that were kept up to date with all the nitty-gritty details. Now, since we become more electronic and everything being stored on computers, I still like to have them keep their data on the computer, but it becomes less important because the files can be moved around more easily. But I used to spring surprise checks of notebooks every once in a while just to keep the students honest and to know that organization and accounting of your data, your observations, is such an important part of research. Because a lot of research, even if you don't discover something new, being able to integrate it with other ideas is really important. It's one thing to get a data point, it's another thing to integrate everything you've observed and to make a holistic overview of a problem. And then, so that was most of our, we've had a great number of undergraduates work with this. A number of them have gone on to graduate school. Some of them have even gotten jobs with our lab after being a co-op student. So that's been very, very exciting. We have a few right now who are very good. And they always bring a fresh perspective, not only to the research, but also how society is moving with regard to what the interests of the young folk are. With regard to graduate students, I mentioned being an adjunct professor at Ohio State in the Industrial and Systems Engineering Department, where a lot of the processing research is being done, but I still have good contacts with the MSc department. Also with the University of Dayton and Wright State University. My main role there has been, besides giving seminars, a lot of the work involves advising MS and PhD students on thesis research, typically on problems that are of interest to the Air Force. A lot of those students have done some very interesting things. We got, and in some cases, that research has been continued after the thesis has been completed. So it's been very nice to have access and to be welcomed by the universities to work with their students. And some of those students also eventually join us, our lab, or in some cases, they've actually been working in our lab and they go back to graduate school. So it's very good that when you have a staff member who has an MS go back to school for a PhD. There's actually a couple of guys right now who are encouraging to go back for PhDs. And not only to these universities, but to other universities also. For instance, one of our students went to Michigan. I know you find that hard to believe, being a Buckeye fan, me being a Buckeye fan, but we'll send a student to Michigan.
If you were going to recommend something to a graduating student, what might you tell them? What would you leave them with?
Well, a couple of things, to wax a little philosophical. When I finished my PhD at Carnegie Mellon, I had a conversation with Professor Lowe, who at that time was, I think, 70 years old, about the age I am now. And he gave me, it's sort of like the graduate, Dustin Hoffman and the graduate said, give me some advice, plastics. In my case, Professor Lowe said, whatever you select, apply yourself and stay out of the politics. Okay, just apply yourself and work hard. So from a broad philosophical standpoint, I would say focus on something that you like and work at it very hard. I think your advisor, Jim Williams, said something similar. He said, all good things come to those who wait, as long as they work their butts off while they're waiting. So I think that's a very important thing to keep in mind. Be patient. And when you enter a field, if you enjoy it, I think, and you apply yourself and you're honest, good things will come to you. With regard to specific technical areas, I think the area of modeling and simulation is still very important. ICME, it's a good framework, but I still believe strongly in doing problems that have a strong industrial flavor and that have some utility to them. So I'm a big believer in doing basic research, but doing that basic research to solve an industrial problem. It's a lot of fun to transition things. I'll never forget Roland Hook from Armco when I was talking to him for Paul's position at Armco. He told me that he really enjoyed the basic research in low carbon steel, but the one thing that he was most proud of was the fact that he was able to develop the interstitial free steel in the lab and transition it to industrial use to make tons of it. And he was challenged because the cheapest alloying element was actually being used. The Japanese had patented it. Okay, so he had to find another alloying element that was not quite as cheap, but he still managed to get the management to buy awful in it. Okay, so but the ability to follow some research from A to Z, I think, is exciting. There are a lot of problems. It's still in aerospace metals, be they monolithic systems. Some of a lot of the work being done in additive is interesting, but I think you have to keep in mind, the transition path or how you're going to transfer. It's one thing to make a shape, it's one thing to learn interesting stuff, but who is the customer? So if I was talking to somebody young right now or a newbie, I would say keep in mind who eventually has to use this. Is it competitive, cost competitive? Does it satisfy a need? And if that's the case, then put your heart into it, do the basic research, and understand what you're doing, and have fun. If you don't have fun, don't do it. I mean, I remember I took one materials course as an undergraduate at Johns Hopkins when I was a mechanics major. It was taught by somebody named Professor Robert Pond Sr. And this fellow, Bob Pond, who later, I had the honor of giving the Bob Pond lecture at Johns Hopkins 10, 15 years ago. Bob Pond had a series of lectures where I think it was called Fun with Metallurgy. He used to wear an aluminum crystal bow tie, but Bob Pond epitomized the importance of teaching and having fun. So I think there's still a lot of opportunity for having fun, be it a conventional or emerging material, being a conventionally emerging process. And so I would strongly recommend people look at the materials field in the future still.
So clearly you've had a lot of fun.
I've had a lot of fun, yes.
So what has been your favorite part of working in this field?
From a personal standpoint, I think satisfying my intellectual curiosity. I'm a curious person. I was born end of December, as I mentioned early. I'm a Capricorn. I don't give up easily. And one thing that I've always kept in mind is how amazing the universe is put together, even at the micro scale of materials or the mesoscale. It just amazes me, and it affects how I approach life. The wonder of metallurgy goes hand in hand with the wonder of life, I guess. I know that sounds a bit philosophical, but it really is true. I have a hard time seeing how anybody who spent years in research, engineering and science, cannot but be in awe of the world around him or her.